can start. So, very happy to have Konstantin again with the second talk, whose title I do not remember, but it had strange duality.
Some duality. I forgot exactly what the title was, but it could be topological dualities in the Ising model. Universally pronounced Ising, but it was German, I believe, so Ising would be correct. And as I mentioned yesterday, it will be about something completely different, but the notion of topological field theory and boundary condition will come up again. In fact, it will be quite important. So I should say this is joint work with M3. It's on the archive, I forgot the number, but it's sometime in summer 2018. And after we wrote the paper, we actually heard from Pavel Sheber, so a lot of our ideas have been sort of guessed by Pavel Sheber, who in fact drew even quite a few pictures much more nicely in his paper than in our paper, but he did it a bit too early, at the time when we didn't quite understand the notion of extended field theory, and we didn't have some basic results on semi-simple tensor categories, which would be required to exploit the pictures. So, so that all ideas. Well, we'll see. Okay, am I going to study this correctly? I think it's this. So I think they were somewhat lost because they couldn't be exploited at the time, and then we very slowly rediscovered them without realizing it. But he has nicer pictures. Can I show you? All right. So what it started out as our attempt to understand some basic algebraic identities in the Ising model, in particular duality. So Ising model in 2 dimensions. First for the group plus minus 1, and then a more general abelian, finite abelian group, and ending with a non-abelian group, and as it turns out, more generally with a finite semi-simple Hopf algebra. So abelian group A, G, and for finite semi-simple Hopf. And so the output, we're just trying to understand that in mathematical language, because the formula you find in physics textbooks are very clear, but after about 2 pages, and this for those trained mathematically, it becomes very difficult to keep track of what is happening, even if you can check all the steps. So initially it was just an exercise to reformulate them in terms of things we know in topological field theory. But the outputs were, surprisingly enough, it was a product that so the outputs were first, we could relate dualities in 2 different field theories in the Ising model in 2D. And there's a famous duality called Kramers-Wannier duality. Also known as highest-low temperature duality. So let's recall what that is. To a duality in 3 dimensions that was also known as the 3D engaged theory. It is known as topological electromagnetic duality. And the relation is simply, as to be precise, the 2-dimensional one lives on the boundary of a 3-dimensional one. Okay, fine, and that makes the statements cleaner, but doesn't do a whole lot. But it turns out it's an output, because as a result, both theories can be made fully extended in the sense of TQFT And now, having done that, you can exploit, and we know that fully extended boundary conditions for three-dimensional gauge theory. It's a result of, I think, Ostrich may have been the first to write down cleanly, but it may precede him. So, we exploit Ostrich's classification of boundary conditions for 3D gauge theory. They're essentially classified by subgroups of the gauge group with central extension, centrally extended subgroups. And by exploiting that, using the fact that we've managed to write the Ising model at the boundary of three-dimensional theory, and conclude what physicists have been claiming for decades, the Landau classification of the topological phases of Ising theory. It implies the Landau classification of topological phases of Ising theory by symmetry breaking subgroups. By symmetry breaking. That's going to be the subgroup. Another output that's maybe of a curiosity, but it's one thing that people who are doing now topological phase also have been interested in and hadn't quite put together correctly, even though they, in fairness, I think they had all the ingredients, just hadn't assembled them correctly, is another conclusion was the extension of this duality, which was known for abelian finite groups to arbitrary groups and Hopf-Alger cluster extension of this duality. Non-abelian mean and Hopf-Alger cluster. Just to say a little bit of what we mean by that. I'll remind you that second order KW duality is it's essentially a Fourier transform, and the thing is now we know how to extend and even categorify the Fourier transform for non-abelian groups, and becomes the Morita equivalence between tensor categories. So between the category of G-grade vector bundles, so vector bundles on the group G with the group multiplication, and the category of representations of G with the tensor product. In the case of a group plus minus 1, you're talking about the same thing on both sides, of course, because actually when G is abelian, representations of G can be identified with vector bundles on the containing dual group with convolution. But the duality does not arise by identifying the original group with a dual group. Not even in the case of plus minus 1 when you have a canonical identification. But that's not what duality says. That's not really important. So I think what we had is once we stated all these formulas in the context of field theory, we understood it had to do with simply categories of finite group action, something like of that sort. It became obvious what the correct generalization was. I don't know if this has any applications, except you can construct a lot more toy models to test dualities. The first thing, the Landau classification of topological phase, confirms what physicists have been claiming for a long time. But in a sense, we don't have, I may say at the end, we don't know how to draw the phase diagram of the theory. We don't know how to say what structure constants would lead to what topological phase of the theory. So that's an open question. So we can tell you that this is a complete list of topological phase vectors. I have to explain what all these words mean, and that's the rest of it. So in the paper I wrote, you actually can find very explicit formulas. They get very long very quickly though. So I'll try to stay at the level of explaining the story rather than writing the formula. So the story generalized in higher dimensions, but then it becomes less explicit. So it's harder to write these. So I'll stay in 2 dimensions. So let's look at lattice models. Lattice, what are they called? What's the difference between lattice models? I think statistical mechanical models is the term now. StatMech. Lattice models. In 2D, and it's easy type. We have another one. So the starting point is going to get space-time as a surface. We'd like to do quantum field theory on it, but we can't quite do that. It's a bit too difficult. Actually, we could do something. So use a simplified model where we subdivide by putting a lattice in some way. So we have a surface S. So the surface is a lattice. And the lattice has a vertex set, an edge set, and there's a face set. Okay? And ordinarily you would have fields at every point of space-time, so but your point of space-time will just be V. So the fields, they live on V. And the interactions should happen along the edges. You always want the theory to be local, and the simplest way to say it's local in this setting is to say that interactions happen only between nearest neighbors. People study much more general methods where you models where you allow maybe to travel a finite distance away. So where this point will interact with that one by means of various routes. But the Ising style models only have nearest neighbor interactions. So we're going to define a path integral from a measure which is going to be used to define a path integral on the space of fields. So the fields will be valued in a group, a finite group. Everything is finite. G's, I'm going to write A for abelian, and plus minus 1 is the Ising case, the classical Ising case. Classical, not in the classical physics sense, but classical in traditional, And the interaction is, you have to specify it, it's a function of the group. And it's trying to keep the values of fields at nearby points aligned. Physicists call it a ferromagnetic type interaction, one which favors aligned positions, but doesn't quite prohibit mismatches. So if you really prohibit mismatches and you're forcing the field to have a constant value, it is not interesting. So the Ising action the function theta from the group to R with positive value. So think of it as an exponential of something. And later we'll require that the Fourier transform, because it will be, the duality will be a Fourier transform. That theta check is also positive. If you want to have fun, you can check that this implies that theta has a maximal value at the identity point. So that's what this is called ferromagnetic type interaction. And now we define a measure. So the space of a measure on the set of fields, classical fields, which are maps, let's call it X to the vector, maps from the vertex set to the group A or G, whatever you want. So X in G may be this way. and namely the measure at the field configuration x is going to be the product over all edges of the interaction which measures how they differ. So it's going to be the product over edges of theta of d plus of e divided by d minus of e. So 1 bar of x of, so the edge has two vertices, two endpoints, so the value of x at d plus e times x inverse at d minus e. And since I don't want to orient these edges, I'm also going to ask that theta should be even. So theta even. Theta of g is theta of g inverse. And then actually it doesn't matter which one is plus, which one is minus. And for the group plus minus 1, the function theta has values either plus minus beta in the physics literature, and beta is identified from the point of view of this mechanics to 1 over the temperature. And what does it mean? So low temperature, what does low temperature mean? Means very high value of beta. So you see that interactions where the fields agree are very highly favored. You get large values when nearby fields agree for their measure, and very low values when the fields disagree. So you're weighing the field configuration. Low temp favors strongly the line field configurations. Whereas high temperature is a bit more tolerant of mismatches. The high temperature is more tolerant. Okay. So having defined a measure, you can now define what I call correlation function, just like in quantum field theory. So define first the partition function. So we can define from here the partition function of the theory. It's going to be the sum over the field configuration, so sum over x, the x's, in a to the a g to the t if you like, of mu of x, I guess. Or you can define correlators. Well, how would we define correlators? For example, you could take a function on the group at some point. So choose some points, choose vertices ik, and functions fk on the group on G, and look at the expectation value of f. This will be called unnormalized correlation, the same sum, so measure, but now of course weighted by the product of the functions at the values of xi, fk of xk. So sum over x. So then averaging the possible values with respect to the measure. And it's traditional, especially when the group is plus minus 1, to reduce the correlation to a set of basic fields, some basic correlations. From what are called, just introducing terminology so that if you ever run into a literature again, you know what these things mean. They mean easy things. From order operators at various points. What's an order operator? It's a choice of a point, so just a vertex, a near of G, non-trivial, otherwise you don't non-trivial of G, and a vector inside. And the choice of vector is kind of concealed because in the abelian case you don't need to choose a vector because after all representation is just C with an action, we have just the vector 1. And can skip the vector. So that's one subtle thing that it's easy to miss when you go to multiple vector in abelian case because the representation is one-dimensional. And when the group is plus minus 1, in fact, there's only one non-trivial character. So in fact, I don't even have to specify anything. I just have to specify the vertex. So for plus minus 1, have a unique for the group plus minus 1, have a unique order operator at each vertex. And every function can then be produced by taking sums of products of order operators at different points. And in the higher rank case, doing some contractions. So can get all the integrals against mu. Now, in what way is this something like the quantum field theory? Well, because it propagates a space-time. So if you take, for example, a surface with, say, two end circles, one initial circle and one output circle, and you put a lattice on it, which means you subdivide the circle to the beginning and the end. And you have a lattice somehow. Then you can essentially use a measure to define a linear map between the space of functions on fields at one end to the space of functions on fields at the other end. So the Hilbert space, the initial Hilbert space, are functions on G to the vertices on the input circle, and there's a map to the output Hilbert space, which is functions on the field configuration, the possible field choice on V on the output circle. And it's finite dimensional simply because G was finite and finally many points, and computing this propagator may be tedious, but it's just a matrix that you're computing by summing over all possible fields in sum. So it's a bit like, it behaves exactly like a topological field theory where I put extra data on the surface, but the data, instead of being something like a spin structure or some other characteristic class or something like that, the data is actually a lattice or a graph. So it's like a topological field theory for surfaces that carry graphs on them, and when you glue two things, you have to match, of course, the vertices where they glue, so that you can get a lattice on the uniform surfaces. So field theory QFT for surfaces, for lattice surfaces. And that's a helpful convention, but you usually normalize. So what you're getting here, because the series of discrete steps is a bit more like an exponentiate Hamiltonian, not like the Hamiltonian itself. And you usually want your Hamiltonian to have the vacuum sort of lowest energy at 0, and then have energies above that. So then it might make sense when you work with it, normalize the operator. So the top eigenvalue is 1, is x for the Hamiltonian, and the other eigenvalues are less than 1. So you propagate for a long, long time, you end up projecting onto the vacuum. That's something you would recreate to imitate what happens in Euclidean field theory. So you can normalize. And you have to be a bit careful because you have to normalize it. You only allow to normalize once and for all. You can't normalize for every choice of surface by in different ways, because that would be consistent with gluing. So it's equivalent to normalizing the measure correctly. You can normalize again. And it's an optional step in a way, because you can ask instead what's the top eigenvalue instead. You can normalize to get top eigenvalue 1. For convenience. And now I'm going to bring forward two things which are related in this case. So I should say the Ising model plus minus 1 in 2 dimensions, and R2 is completely solved explicitly. So almost any discrete statement you want to make is either has been proved or something close to it has been proved and checked. But when you go to other groups, much less is known. I mean, almost nothing. There are some guesses based on numerical calculation. When G is not plus minus 1, you can only make some guesses. So what happens here? So first of all, the first thing that happens is something you could guess. So 1. So if the temperature is low, so if T is small, so beta was large, these are strongly correlated. So what you might suspect is that the measure is concentrated on field configurations that are almost constant. And well, in any finite system, it's very hard to make a qualitative statement. But what you can try to do is to go to a very large lattice or make the lattice very dense on the same surface to have lots and lots of points. That's what the thermodynamic limit. In the thermodynamic limit, the measure concentrates on the two configurations of constant spin. Plus 1 and constant minus 1. So what that means is that in fact if you make the lattice large enough and you look at, so if you like, pick random samples of fields, you're going to get that it's mostly positive with some small islands of negative spin, or mostly negative with some small islands of positive spin. So whereas,
can you remind me what T is?
T is the temperature, is 1 over beta.
Yeah.
T is 1 over beta, and that means that theta is very large when xi is xi prime, and small if not. So very high weight for a line configuration, very low weight on mismatch. And high cost, if you like, to energetic is high cost to making spins mismatch within the body. And intuition tells you this is what should happen, and 2, if T is large, then this order dominates. There will be infinitely large areas of either sign of the spin in the big random configurations. I'll make a more precise statement in a second. That's supposed to be. So in other words, the coupling is no longer powerful enough to overcome the inherent randomness in the system. I think just too weakly correlated to be forced to allow large scale to agree. So you might think, okay, that's intuitive enough, but actually it's not trivial, because if you try the same thing in 1 dimension, using model on a line, that's not true. What's true in that case is that if the temperature is 0, yes, you're forcing everything to be aligned, either all plus or all minus, because everything is forbidden. But as soon as you start moving on temperature a little bit, you might as well have made it infinite, it's all hot. And somehow, a posteriori explained by the fact that if you have a chain of, say, pluses and minuses at the outer ends, the only constraint happens at the ends, no matter how long the chain is. And in that chain has large entropy because a large space of state. So if you make the line segment very long, the energetic cost at the end for keeping things aligned cannot overcome the natural tendency of randomness. I think it's a beautiful physics argument explained in the book by Carty. This being said, physicists believed initially that what happens in 2 dimensions, of course, the region will have an actual boundary and the energetic cost increases with the size of the boundary. So this being said, I think it was believed in by Ising that the same 1-dimensional problem or bug occurred in 2 dimensions, and was discovered by Penn later by a clever argument that no, in fact, 2 dimensions are different, the difference between low and high temperature. So when you move the temperature between low and high, something funny must happen. There must be a transition. So what we say is that phase transition at the critical temperature corresponding to a value of beta, and the value for a square lattice, the value is such that psi sinh, sorry, of 2 betas critical is 1. And actually, if you want to do a quick exercise, that's a value of beta for which the function e to the beta and e to the minus beta on the group plus minus 1 agrees up to an overall scale with its Fourier transform.
This is square lattice on the sphere? Or?
Square lattice on the plane.
Okay.
So that you can make it large, it's uncontroversial what that means. So if you want to think maybe of a torus, so you spelled out the boundary conditions precisely, it turns out the boundary conditions don't matter if that is large in this kind of model, largely because of the decay of the interaction. So if you're in the middle of a region and the boundary is very far, what happens there is not particularly sensitive to the boundary. That's not a general fact, it's specific. So let me state it slightly differently in terms of this propagation. This is the Hamiltonian. So at low t, as the number of points on the circle increases, the number of lattice points on x1 increases, the Hamiltonian approaches the projection onto a two-dimensional space, the two spaces of constant spin. The function of the two spaces where the spin is either plus 1 or minus 1. Projection on, let's say, C plus C minus, there are spaces of constant spin, or configurations. Constant. What is that? High T. It converges instead to projection of one-dimensional space, which is a constant function of all spin configurations. No spin configuration is stable. Projection on C with constant function all spins. So randomness prevails. So that's a field theory restatement roughly of this. So again, there must be some transition when you play with the temperature between these two states, because as you can see, the vacua, so to speak, for the two theories are very different. There must be some place where if you look at the top eigenvalue, it must transition from projection to from the eigenspace, from this eigenspace to the other eigenspace, so somehow that's kind of crossing of eigenvalues happens. And that turns out to be an interesting point, because it turns out to be an example of a second order phase transition. There's a definition in physics in terms of various quantities, you can define them thermodynamically, but what means the following? This is almost, well, it's universally believed, I'm not convinced it's a complete mathematical proof, but it's a universal belief. Maybe it's a disproof of any possible alternative. Universal belief in the continuum limit, when we start making the lattice infinitely dense, the Ising model approaches a quantum field theory, and that's one that's very well known, the free fermion theory. And the parameter beta, which actually you have to keep moving in order to take the limit, corresponds to the mass. And beta critical corresponds to massless fermion. And that's a conformal field theory. Whereas any other value of beta corresponds to a massive fermion, and they're distinguished by the fact that there's a spectral gap between the vacuum and the rest of the Hilbert space of states in the massive case, and there isn't one in the conformal case. And that's roughly correspond to the second order phase transition. I mean, to pass through a conformal field here. This duality, by the way, changes the sign of the mass, and the mass is coupled to a Clifford generator that actually makes sense. Maybe I don't want to spend time explaining more about the correspondence, but at least there's huge experimental evidence and some theorems about what happens to correlation functions that this ought to be true. The precise sense in Gelati's theory becomes a common field theory is not, I don't think has been formulated very clearly. But it's something we know what happens. Okay, now the mystery with all this background. In spite of this apparent difference between high and low temperature, in fact, the theories are meant to be equivalent at high and low temperature. So KW duality, equivalent between Ising model at beta and beta check, where beta check, beta raised by sinh to beta and sinh to beta check is equal to 1. And we need to use Poincaré duality on the surface in the form of replacing a lattice with a dual lattice. And with the dual lattice on the surface. So edges actually correspond to edges, but they're normal. Vertices become the new faces and so on. So V is V check, whatever V is V check, V F check faces. Faces V check and E correspond to E check, but like this way. These are new edges. Old edge.
But this is purely combinatorial, there is no metric statement here.
There is no metric in this one. There is a numerical parameter beta, but there's a formula for changes. And actually, this is just, I'm not sure I'll be able to write all the formulas the way they're going, but it's going to be an institute of Fourier transform. What I want to explain instead is, because I think this is the idea of how you reconcile that statement with what I just said here, where I said at low temperature are the two-dimensional vacuum space, and high temperature is the one-dimensional vacuum space. It seems impossible, right? So something is wrong. And what's wrong, or not wrong, but and that was known actually. It's not our discovery. It just wasn't stated in a way that was making it instantly recognizable. And the observation is that the Ising model has a symmetry, has a global G symmetry, G being a group. If you translate all the fields by G, the action is preserved, but this symmetry can be gauged. So you can couple, instead of saying that the fields are functions of the group, you can see the sections of a principal G bundle on the surface. So can replace, let's see, couple to principal G bundle on S and take fields to be sections on V. Over V. And once you say that, you notice that in fact you don't even need a principal bundle to be defined on the whole surface. You just need to be defined on the one skeleton of the lattice. You can allow ramification in the centers of faces. That's going to be important. And you can allow ramification in the centers and those are the objects in the physics book you'll find under the name of disorder observations. So some order order operators have as a label the representation of the group, and disorder operators as label the group element, it tells you the ramification on the point in the center of the face. So you're beginning now to suspect the duality here, to replacing an irreducible representation of group element is beginning to look familiar or remind you of what I said about the tensor category of representations and the category of raised vector bundles.
These are bundles with a connection.
Sorry?
These are bundles with a
The
connection.
G is a finite group, so yeah, sorry.
Okay.
Early at the beginning, I think G is a finite group. It's just a finite, completely finite moment. Yeah. So, if you like, this ramification in the center is the analog of the curvature in the finite case. It's as close as you can get to a curvature, the curved G bundle on the surface is a good ramification. All right, but now before I state the general statement, let me explain this duality here. So now that we understood that, in the case of, in the Ising case of a group plus minus 1, or plus minus 1, there are two bundles of the set. So there are two circles, really, not just one. And there is also a symmetry, plus minus 1 action on the space of states. The global change in all the space, which preserves everything. So what we have really a tableau of four things, where we have, it's a trivial bundle and a Möbius bundle. So these are the bundles, and these are the representations. So this is plus minus 1 action, which is trivial and the sign representation. And in the cold temperature region, well, on the trivial bundle of the circle, we do have two vacua, and they're interchanged by the symmetry. So you're getting one copy of a trivial representation, one copy of a standard representation. And it turns out, if you look at the Möbius circle at low temperature, there is zero space of vacuum. How is that possible? There's always the lowest energy space, but the lowest energy space, if I have a Möbius thing, cannot have constant spins everywhere. Somewhere it must have at least a jump. So the energy of that is higher than the energy of the vacuum on the trivial circle. So it is not a ground state for the topological limiting theory. It's actually higher energy propagates. So that's where we get nothing in this case, in the cold case. But in the hot temperature, the same thing here. Then inside, what did we just say? On the trivial bundle, we got one vacuum, the constant function on all spins. That obviously doesn't change under the symmetry, so it's a trivial representation of the group. And the Möbius case, we also get the constant function on all spins, which is no worse energetically than the constant function on all spins on the trivial bundle. At this point, it stopped caring. So there are two vacua also, just they're distributed differently. So what happens is that the topological type of the bundle and the character of the representation in the vacuum space get interchangeable. So this is a duality, if you like, on vect in the category of S2 unequal, sorry, Z2, on vect Z2 of Z2. The Z2 is the stack of flat bundles on that Z2 bundle. And on that there's a Fourier transform which implements exactly what we've seen.
Oh, wait, in that notation, what are the arguments?
Which
In the
notation?
Bax notation?
So Z mod 2 is a monodromy.
Oh.
So I'm on the G equivariant vector bundles on G.
Oh, okay.
With them right. So the monodromy and its residual group action symmetry. And actually, since I've written that, vect G of G is a category, which three-dimensional G gauge theory associates with a circle. Through S1. So three-dimensional field theory on a circle, you get a category, and that's a category. And the Ising ground stays an object in this category. And what's happening with the hot and cold is that the rows of the two G's get interchanged, and that is what happens in 3 dimensions, like that y. So let me tell you that story quickly. So maybe some quick review of 3D gauge theory. Finite group. So, three-dimensional theories are generated by tensor categories, right? We take the tensor category to be vector bundles on G with convolution. And so that's associated with a point. S1, I just tell you, is a category, is a Hochschild homology, categorical Hochschild. Let's actually say it. I can afford to be sloppy here because this is in fact unoriented theories. I don't have to be careful about orientations, framings, or anything. The circle corresponds to the Greenfeld center of P, which is the G running vector bundles on G. Well, surface, closed surface, to make it easy. We associate the space of functions on band G bundles on sigma, and to a 3-manifold and 3 closed, we associate the total count of that bundles, weighted by the automorphism, the sum of the 1 over all. P over isomorphous classes, P over M isomorphous classes. Now, in this theory, because you have a classical underlying theory, you can sort of build it, if you like, by hand. I can tell you how to construct everything. I didn't tell you what to do if you have a surface with corners, but you could write down exactly what to do.
What's the significance of the angle brackets?
I want a group ring somehow.
But it's not like you're taking this category.
It's on the group, but the convolution, I wrote it twice maybe. The multiplication is convolution of the group, not pointwise.
No, that I understood, but
that's all I said. That's the only thing.
but it's still a groupoid. You're not allowing homomorphisms which are not isomorphisms.
No, the category, that's right. The category is just vector bundles on the group, on the group as a set. That's correct. So I mean, if it makes you happy to put.
No. I was just no.
Just vector bundles on the finite set. That's a category, and the tensor structure is convolution.
The tensor structure is the convolution.
So that's what I want to indicate in the angle bracket somehow, because when I write vector on a set with brackets like function in a space, and it's a pointwise multiplication, and that's all. I've gotten rid for this before, I should confess. I should change my view. But let me point out that for I and 0, give a construction from a T, a tensor, let's say finite, semi-simple, and there's a word I don't want to explain too carefully, spherical category, tensor category, with internal duals think the official term nowadays is probably spherical fusion category, spherical multi-fusion category. They initially constructed 3D T2FT in the old Salatia sense, but now we understand that what they really did was give a construction of a fully extended T2FT. So now it is fully extended. An abstract construction. And it's abstract in the sense that in general it does not come by quantization of a classical theory. In the special case of this tensor category, or producing gauge theory. But it's usually not. The vector space is usually not a set of functions on a space of fields. A space of functions. Say space of functions on a set of fields. It's constructed just from a tensor operations. And the theorem, which now is called electromagnetic duality, I don't quite know what names to put on this. It comes from physics initially, but of course you have to supplement it with lots of work from this combinatorial category theory, is that rect G with tensor product and vec G with convolution give equivalent equilibriums. And that's more or less clear once you understand you can construct TFT just from a tensor category, because these turn out to be Morita equivalent categories. So that works. There would have been a much more complicated way to describe all this just by using a tensor category structure. But now let me introduce two more things in gauge theory, because they're easy to introduce here. And I'll tell you as an abstract definition that I won't have time to give. Observables in 3D gauge theory. And there are no point observables, there are no fields you can put at a point to compute something. There are line observables, there are line observables. There are Wilson lines. Proof lines. So the closed manifold, it's easy to say again because the theory is obviously by quantizing some of the finite classical theory. Time to read the books. You can choose a loop inside, or link in fact, labeled by representation, and weigh the count of bundles. Wait. By the trace of the harmony along the loop. Trace of the harmony to get the new invariant, to get the correlator, if you like. The loop is abelian depends only on the homology class, of course, of the loops, but if it's not abelian, it gets more interesting. Depends how they knot each other. The tooth line, again, in the closed manifold, you have a loop, and the loop is labeled by a loop element. And what you do there, instead of counting bundles, you're counting ramified covers, ramification around that loop with monodromy around the loop given by the loop element. You count ramified covers. So I'll just tell you without demonstrating that these operators can be defined abstractly. Actually, let me make sure I say it correctly. So fact, let's say, given, maybe it's a theorem actually, given a 290 style tensor category T, so a spherical fusion tensor category T with a fiber functor faithful tensor functor to vector. One can define loops and Wilson loops, Wilson operators. So, and the duality ref G, ref G, the two operators are interchanged. What happens, each of these has a fiber functor, so actually I'm rushing a bit. The ref G has two natural module categories, the fiber functor vector and the category as a module of itself. And the same here, we have a fiber functor vector and the category as a module of itself, and these guys are interchanged by one. So the rest of the pops. And then let me state the final theorem. Oh. I should mention here my theorem of Ostry. This must be the category of representation of a finite single top particle. E is H mods of finite. The theorem is that the Ising model for G gives a boundary condition for 3D topological gauge theory, and what I used to call the order operators in the Ising model are endpoints of Wilson lines which end on the boundary surface. The order operators endpoint of Wilson lines. So these order operators I mentioned are the endpoints of lines. And 3D electromagnetic duality, in the abelian case, it corresponds to the Kramers-Wannier duality. So in the non-abelian case, the other side is new. It's a categorical Ising model built from a tensor category. So non-abelian case, it's a new, it's like purely quantum Ising model. There are no classical fields going with that. Yeah, I want to stop here and just repeat what I mentioned at the beginning. If you're asking what happens at the thermodynamic limit on the boundary, well, if there's any reasonable way to take a thermodynamic limit and extract the lowest eigenspace of the topological field theory, that field theory must be a boundary condition for 3D gauge theory. And those are classified. So we know what possible DQFTs can come out from the thermodynamic or continuum limit of these moments. And what's open is we don't, in the Ising case, know which value of beta gives what. In the more general case, we don't know how to start from a function on the group and tell you this is the theory we get. I think it's an interesting open question, trying to find the phase diagram, which actions on the group which drives to which topological field theory is in the limit. Stop here.
Thank you. Questions?
In this picture, what is the critical beta corresponding correspond to? The phase transition?
The phase transition corresponds to a self-dual point of the Ising model, so that makes sense for Z2 because Z2 and its dual are canonically identified. For a more general abelian group, before you can talk about the self-dual point, you have to choose an isomorphism in the group and it's Montiagan dual. And then you can ask about which actions are self-dual. And for example, if you do Z5, it's a line of such things. So spec another phase diagram for Z5. It's a rhombus. Because if you put the parity condition on the functions, that it's even and real, then you have only two parameters and the positivity condition that are something like this. And the duality sort of is a reflection on the space of action about a line like that. There's another reflection which is the outer automorphism of Z05. So it's a kind of Z2 cross Z2 symmetry in the model. And in that case, it is known that this point here in the center, which you might be very hopeful about, is not a conformal field theory. It's what's called a first order phase transition. Let's say the one topological theory takes over from the other. But they are suspected to be topological conformal theories at the corners, but no shadow of a proof exists. So I mean, there's some claims that phase diagram is supposed to look like that. And numerical simulations support that. But yes, so in this case, there is a dual point which is also a phase transition. But it's where you have two topological theories embedded in that. The eigenspace move, and at that point they agree. And of course, symmetry switches them around.
What if you take a theory in which the local interactions are given by difference operators? You know, like these Cairo-Potts models.
Well, Potts model is a special case of this. So the Potts line would be this.
So you're just changing the
This
group?
interaction. No, it's the group Z5 in this case. And in the Potts model, you're only allowing functions which are linear combination of the delta function at the identity and the constant function of the group. So it's a special case. The Potts model is a special case. And that has been studied at least numerically enough, and we know that after 4, we don't get conformal field theories at the phase transition. So you can tell what the phase transition point is. There's only one phase transition on that line, and it's first order. That one seems to be known. I mean, it's hard to say what's known. There's a lot of knowledge which came from physics as a result of massive numerical calculations as opposed to theorems. So.
No, but I was asking more like, you know, if you take your, I mean, here you're looking at, you have a group, right? But then you are looking at arbitrary interactions basically, because you're allowing arbitrary functions, and the interaction term is anything you can prescribe. But what if you put a constraint on the interaction? Will the theory become more symmetric, less symmetric, more?
Well, I mean, if you happen to be on a line that's preserved by the symmetry, then you can say something. But if you constrain to just want to study this line, that wouldn't be so helpful because
it doesn't. The symmetries don't.
Yes, but the Potts line does preserve the symmetries. Yes, so you're changing the delta function at 1 with a constant function.
Any other questions?
This is kind of a jump, but can one explain black hole thermodynamics by putting Ising model on the horizon or the two-dimensional boundary?
You must be mistaking me for my physicist twin brother. Sorry, no, I have no idea. I don't have a physicist twin brother. Sorry.
Okay, let's thank Konstantin again.